Good. So we can start, I hope.
Yeah.
Yeah, it's a pity that I cannot see all of you, kind of like talking to myself, but I hope it will not be boring anyway. Welcome to today's first talk. We are now testing the online mode, and I hope with other participants it will then go much easier. Of course, it's much better to be present in person, and I'm really sorry that I do not have a possibility right now to join you in person because you're such a wonderful community, and it's always very pleasant to be in one room with you and to enjoy the atmosphere. From the topic of my talk today, we're going to be to stay pretty theoretical. And in the afternoon, I hope you will get some more practical information on this topic. And maybe if it's completely new for you, it will become more clear. So my name is Dariia Strelnikova, for those who do not know me. I'm a senior researcher at the Carinte University of Applied Sciences in Austria. I belong to the research group called SIENA, which is the abbreviation for Spatial Informatics for Environmental Applications. And as you can hear from the name of our research group, we're dealing with different environmental applications, not only with flow monitoring. So we're not hydrologists in that sense, because our area of research is much wider. So we're applying drones to many different domains. And some of our research includes monitoring of rivers. And I would like to talk right now about the theory and methods of river flow monitoring with drones. So give just some theoretical background to the topic before we can move to some more practical applications. What will be the structure of the talk today? So first, we will discuss some reasons for flow monitoring and the approach to methodology. Then we will go through the general workflow, which is comprised of 4 major steps: data acquisition, pre-processing, processing, and post-processing of results. Then we will devote a little bit of time to the validation and to the limitations of river flow monitoring with the US, because any methodology that exists in the world is not perfect. So there are always some limitations to it. So let's dive in. What are the reasons for flow monitoring? Of course, the main idea is people like to understand and control things around them, and the regulation of surface and groundwater levels are naturally the important idea that motivates the flow monitoring. This leads us to the possibility to prevent disasters, or at least to minimize their negative impact. We have been affected in Europe by very severe floods in the recent weeks here in the north of Austria, in Poland, and some other areas. So, of course, it's very important if we can minimize the effects of such events, or if we can prevent them in the best case. But not only floods, also land erosion, landslides can be prevented, or their impact can be not that severe if we understand and properly manage the water flow. Then, of course, there is supply of foods, which depends on water flow. And this is twofold. On one hand, of course, we're talking about irrigation, the understanding of how much water we have for the irrigation. On another hand, the river network is an important transportation network in many countries of the world. So again, it all should function properly for us to be able to get enough food supply. Then there is hydropower production, which is closely connected also to the environmental issues. On one hand, this is clean energy. On another hand, of course, hydropower dam introduce some obstacles for the migratory animal species or fish species. And on one hand, we need this hydropower, and we need to understand how much water do we have to produce it. On the other hand, we need to understand how much water can we also use to remain, or to be remained for the downstream habitats. And there is a less maybe important topic of aquatic recreation, but it's also a big field of human activity. So for this, we also need to monitor flow to understand the flow. And since there are so very many important domains of application of river flow monitoring, there are, of course, many methods that existed hundreds of years ago or many thousands of years ago. and they continue to develop. And we're not going to discuss all the possible methods in this talk, but we will focus on the most modern techniques, namely the application of drones and image velocimetry techniques to measure flow from acquired videos, drone-based videos. What is image velocimetry? It's just measuring velocities from images, from sequences of images or from videos. And when we apply image velocimetry to measure flow, we need to measure the velocity of the flow, and therefore we need something that we can trace in the flow, something that moves with the flow with the same velocity. From these traceable features, we can derive the information about how much or how fast the flow moves to. The general workflow of image velocimetry with drones for the river flow monitoring involves 4 stages. The first one is data acquisition. Here we select our study area, how large it is or should be, what is the camera angle which allows us to capture the information that we want to capture, what is the target spatial and temporal resolution of data that we're going to capture, which drone is suitable to capture the data that we need, which sensor do we need, are there any traceable features within the flow, and if not, which artificial tracers can we use? And then at this stage, the data capture itself is being done. When we have the data, we start pre-processing it in the second stage of the workflow. Very often we need to subsample the data. We do not use all of it. We need to stabilize images because drones, they are not very stable inherently, and the imagery is very often shaky. Then there are some distortions introduced by camera angles or lens parameters, which have to be removed. There is masking out of irrelevant areas, and there is image enhancement. Then there is the data processing stage, where we select the suitable method of data analysis and apply it and calculate velocities based on this methodology. And after that, when our calculation is complete, we see whether it makes sense. Does it contain any spurious vectors? Does it contain any outliers that have to be removed? We can also interpolate the data, especially if we remove some of the portions of the data, since we see that this data was calculated wrongly. In these areas where now we do not have vectors, we may use interpolation. We can use techniques like smoothing and aggregation. And of course, in this stage, we visualize results to see whether it makes sense, and also to convey this information to our stakeholders, to our readers, if we publish our research. So we will now discuss in more detail the data acquisition stage, which starts with general considerations, what we have to have in mind when we use a drone. So of course, we have to comply with legal requirements. It doesn't really matter for what we use a drone. There are regulations that we have to be aware of and with which we have to comply. It doesn't really, unless probably we're police in some country which has their special rules. Everyone else has more or less the same rules to obey. And then, of course, we take care of the environment. So we try to not disturb any wildlife with our drones. We also use them carefully because we do not want our drone to fall into the river and hurt the environment in this way. We have to respect people's privacy. Very often this is in the law, but not everywhere. And of course, we wouldn't want to be disturbed, so we also do not want to disturb other people. We know we need to know the operational limitations of our UAS. How long can it stay in the air? At which temperatures can it operate? At which wind it can operate? And we have to choose only suitable weather conditions. On one hand, from the point of technical limitations of our platform, but on the other hand, we want to collect quality data. And if we have high wind, very often our data will be useless, both because the footage will be extremely shaky, and because we will have a lot of waves introduced by wind, which do not tell us anything about the flow. So if we are ignoring these basic rules at the stage of data collection, it may be that no pre-processing and no processing, no best method will help us to get any reasonable information from this data afterwards. So as we have already mentioned, we need something in the flow which represents the behavior of the flow to trace these traceable features. If there is nothing in the flow displacement of what we can track, then it's not possible to apply image velocimetry techniques. And we can have natural tracers, especially in high flows. There are always some crests of waves, there are bubbles, there is debris, or very characteristic structures. In low flow conditions, very often we do not have anything on the water surface, which represents the behavior of the flow, and then artificial tracers can be used. And these artificial tracers have to be introduced into the water flow in order to collect the necessary information for image velocimetry. So here are some examples of traceable features which can naturally occur in the flow. This can be ice, this can be bubbles, this can be foam, this can be just debris. And if we use artificial tracers, very often these are this must be the tracers which meet the following requirements. So they have to be floating in order to represent the behavior of the flow. They have to have a color contrast to the background. So they need to be well visible within the flow. They have to have passive response to the flow to describe its behavior properly and not to introduce some of their behavior. Then they need to be produced in mass, because if these are expensive tracers in limited quality, in most cases we cannot really cover the whole width of the river, and they cannot produce sufficient information for us to apply image velocimetry methods. And of course, since we're dealing with the environment, the tracers must be safe for the environment, so no degrading effect on water quality has to be associated with those tracers. The common examples which are used in practice and are often described in the research are wood chips, charcoal, which is a little bit less common and more expensive, and ecofoam or void packaging made of corn or of potato. So any kind of biodegradable tracer would work too. And usually the deployment of these tracers is done manually, and we are going to achieve the homogeneous distribution to show the behavior in all regions of the flow which are of interest to us. So you should not underestimate the complexity. Oh, I see the screen has gotten blue for some reason. And now it's back again. And the complexity of tracer introduction into the flow. Then, if we have cleared the question with tracers, there is a question of how do we come from the image space to the real world space, because we want to measure velocities in meters per second and not in pixels per frame. And for this, we usually use the ground control points, which give us information which pixel in the image corresponds to which coordinate in the real world. The plates are, as you can see in this image to the right, I hope you can see those ground control points on both sides of the flow. They must be different from the background and easy to track, and their coordinates must be measured in the field such that we can perform optimally georeferencing or some simpler kind of geometric transformation in order to find the correspondence between each pixel in our image and the real world coordinates. There are also methods to georeference the imagery without ground control points based on the exact location of the UAS during the flight and the camera parameters. But the use of GCPs is still a very common practice, and it's also a very reliable one. Therefore, I do not think that it's completely going away in any near future. But I think that some of the colleagues may introduce other methods to you during the talks in the next few days. So when we have our tracers, we have our ground control points, we need to decide how high we fly. And for that, we have several factors to consider, almost all of which are interconnected. Namely, we are looking at the extent of our study area. So the bigger it is, the higher we probably are going to need to fly to capture all of it. This will, of course, be connected to the pixel resolution of our sensor. So the less resolution we have, the less we will be able to capture with a great level of detail. We have to keep in mind our target ground sampling distance. So how big are our tracers? How can we make sure that they are visible in the footage? And what is the minimum size of structures that must be recognized? Even if we have large tracers, are there any details that we want to see in the footage that require a high ground sampling distance? So these four factors are connected to each other, and the selection of the flight height is always a balance between the available sensor resolution, because we know that high resolution cameras are expensive, and of how much do we want to see of our study area. Do we want to select divide our study area in sub areas then, because we cannot capture all of it? So this is what we're dealing with from the technical point of view. But then there can be also obstacles interfering with the signal or shading the field of view. For example, in our applications, we had to measure flow patterns near hydropower dams. And near a hydropower dam, there are always a lot of wires. So where do we fly? Do we fly under the wire, and do we see less because of that? Do we fly over the wire, and the field of view is partially shaded? Of course, we have to keep safety in mind. We cannot fly too close to the wire. So this has to be also considered when we're planning our flight height. And there may be legal limitations. So let's say we have a large field of view to cover, and we have a very good sensor, but we're still not allowed to fly over 120 meters if we want to stay in the open category in Europe. So this may be another thing that technically everything else works, but from the legal perspective, you will still need to fly lower. And then when this is already solved, we ask ourselves, how long should our videos be? What would be the target duration of our videos? For that, also several factors play an important role, because on one hand, it's tempting to capture longer videos, but we can have a higher amount of camera movement in a longer video. And of course, light conditions can also be changing. Even within 5 minutes, this is very often the case. We're not in the lab, and because of that, sometimes we just need to fly. So the weather conditions are close to optimal, but the illumination is not completely perfect. There are some clouds which are moving, and the longer video we have, the higher is the probability that the light conditions will change over the course of this video, which will influence the analysis results. We need to maintain sufficient seeding density during the recording, and the longer we record, the more difficult it gets to have tracers homogeneously distributed in the flow all the time. It can be easier if we have natural tracers, though those also tend to cluster, so we will not necessarily get better distribution over a longer video sequence. But if we use artificial tracers, very quickly it gets very expensive to record long videos, because even for several minutes, you may need several hundred liters of those tracers, especially for wide rivers. And then there is, of course, a question of price. Then the size of available storage nowadays, of course, is not always or very rarely the issue because storage cards have gotten large. But also if we use high resolution sensors, a very short video, like a minute video, 2 minutes video, is already several gigabytes of data. So this is the question of storage on the platform, then on storage of this data for historic purposes. If you do regular flights and store all the data, you're getting terabytes of data very, very, very soon, and you have to manage all the data later. So there is a question to not produce the data which is unnecessary. And there is a question of analysis. So the more data you have, the more difficult it is to analyze it because it's computationally challenging, and it also takes a lot of time. So we have to think of what would be the optimal approach, the most efficient approach, and not just record as much data as we can and hope that later it will be useful for us. So it's a common practice to record relatively short videos up to 5 minutes and not to use all of them, just portions from 30 seconds to 1 minute. There are some studies which operate longer video sequences, but they are pretty rare. So usually these are short videos are sufficient. And the last point that we have to consider at the stage of data acquisition is the metadata. This is probably a boring topic to discuss because when we work with drones, it's interesting to fly, it's interesting to capture the data, and we really want to get into action as fast as possible. But if we do not record the metadata in time, there is very often a high probability that later we will not remember all of this information, and we will have problems restoring it. So even the location of and the extent of the study area may be later, a couple of years later, if you want to work with the data again, not known, especially if you do a lot of flights. The date and time of data capture seems like you do not really need to record it because you have it on the video, but sometimes there are programmatic errors at video recording, and that time is not recorded correctly. So not in the correct time zone, or with some deviation from, like, several minutes deviation from the original time, because the sensor is set this way. And then if you want to compare it with the reference measurements and you want to be as close as possible, you cannot really say what was the correct timestamp. So it's better to write it by hand right away on a sheet of paper, and then you will have it. Then, with which drone did you fly? What was the sensor that you used? Extremely important. The sensor characteristics, very often you will, or almost always, you will need to remove some lens distortions from your footage, and you need to know which sensor you used. Then which US platform did you use? If you do a lot of research with drones, you want to later be able to compare the results acquired with different drones because they behave differently. And for that, you need to have historic data, which footage was acquired with which drone, if you have many of those. How high did you fly? Sometimes your intended flight height and the actual flight height, they are different. And it's also interesting when you write down, so what was your intention and the settings initially, and then you see the logs, to which extent these correspond to each other. So this allows you to plan better in the future. Then the weather conditions. Sometimes some errors are produced in the analysis, and they cannot be attributed to anything unless you see, okay, the weather conditions were unsuitable. And then later you can see that for certain weather conditions, you have similar errors in the analysis. So right away, write down what was the weather, not necessarily in very much detail, but it's very useful. And of course, all of this metadata, if you tend to later publish your research, they are all useful to describe in your study design, because this is something that everyone else will understand and will be able to either repeat or avoid if your results are not that satisfactory. Then if you use GCPs, you need to record the coordinates of GCPs or the distances between the GCP markers. The distances we measure in cases where we do not have high accuracy position measurement equipment available. In these cases, and when the width of the river allows us to do this, the distances between GCPs may represent a better option for later auto-rectification of the imagery. Then we use some tracers, and if these are artificial, we know how much did they cost, what are they made of, what is their color, and so further. So all of this information can be later very useful during the analysis of the information. And if you make any reference measurements simultaneously with your flight, these also have to be recorded thoroughly in order to later be able to assess, to validate your analysis result probably. So when all of this is done, we're done with the data acquisition stage, and we capture our data, and then we move to the pre-processing of data. So we have it, and what do we start with? First, of course, we have a lot of data, maybe like even 5 minutes of data may be too much for what we want to analyze. 5 minutes times 60 frames per second times 3,600 seconds in each minute. This is a lot of frames, and not necessarily all of them contain optimal tracer distribution or optimal displacement between the tracers. Because for many image velocimetry techniques, especially for particle tracking velocimetry, we need certain minimum displacement between the features in consequent frames in order to be able to derive meaningful trajectories. If this displacement in sub-pixel area, then very often we will produce wrong measurements from such low displacements. And because of that, we need to subsample, so take every third, every fifth frame instead of every frame, in order to get better displacement of it. And also it will reduce the computational load. We will have to perform less analysis, and we will be able to get better results. It's not very easy to get or to find the optimal subsampling rate if we have heterogeneous flows where part of the flow is fast and another part is slow. But in most cases, subsampling makes sense. So selecting each nth frame and also taking not all the footage, but the part of the footage where we have the best distribution of tracers is very advisable, because if we add footage with bad tracer distribution, we produce a lot of outliers, a lot of wrong vectors, which we will have to anyway discard later on. So it's better not to produce them in the first place. So after we're done with subsampling and we have our target data set the way we want to see it, we have to think of stabilization of it, because drones are inherently shaky, and it means that even if there is no strong wind, we will have some displacement of motionless features in our footage, which has to be removed first because it, of course, biases the velocities. So there are multiple different stabilization methods, and in most cases, you're not developing in U1 when you work on such a project. You're just taking a software which already can do it, and you make sure that your original shaky footage, after applying a tool from a toolbox, is stable, and the only thing that moves are your tracers and not anything else. Then, of course, you have very often distortions associated with perspective. If you have oblique camera angles, which was the target of your study, or if it's unintentional. This also happens if you want to create an RDR footage. It doesn't always work this way. And there are lens distortions. Modern sensors very often undistort the imagery right away, programmatically, but it's always useful to apply a camera model for the undistortion process of lens distortions, to make sure that your footage is really correct and not having any distortions at the edges or any scale problems associated with the lens itself. Auto rectification, so making sure that the scale is true and that everything is at nadir in your footage, is the best option anyway, because even the small differences from nadir, so for example, you have set your drone at nadir recording, you have selected a sensor that you know that it undistorts the images automatically. You cannot still guarantee that your recording was all the time at nadir. When you perform later an auto rectification, very often you see that a small change in angle is observed during the recording, especially in longer footages, and even a very small deviation from nadir. So in the research of Detert, for example, even 2-degree deviation can produce very strong bias in, especially at edges of your field of view. So every time you can go for it, go for auto rectification, despite the fact that it may sound complicated, and especially since many tools today support it too. Then, when this is done, we come to the stage of image enhancement, which includes both application of different filters, which help us to make tracers more visible and get rid of the noise that we do not need. But also at this stage, we mask out the areas which are irrelevant for our analysis. This masking out, of course, has to be done after the stabilization, because if we mask out something in an unstable footage, then after we stabilize, something will be masked out despite the fact that it was actually the flow that we're interested in. I'm not going to go into very much detail which filters exactly exist. If you are interested in these details, in the chapter 9 of the book that was recommended for this course, there is some information on different filters, how exactly they work, and in which cases, which of them are useful. But the main point is that every filter that you apply is necessary in order to make the traceable features more pronounced and everything else less visible. So sometimes it's just a question of trial and error. Very many different or several image velocimetry suites include different filters, and you can just test it and see what works best for your particular case. And there is also an option of background subtraction. This is when the background is calculated. Especially this is very good for visible river beds where you have a lot of background noise. And then you get basically only the traceable features and the background is away. For turbid water, it's less common practice because background subtraction doesn't really result there in very good removal of noise. Then, after we have performed the image enhancement, we are ready to move to the data processing. And at this stage, we need to first select the method that works well for our particular case. So there are two classic methods, which are particle image velocimetry and particle tracking velocimetry. They are studied in the recent 30 years so thoroughly. There is plenty of research on these methods, both in lab and in field conditions. In the recent years, some optical flow methods, new optical flow methods, are being applied in the field too. And when we want to select a method, we have to first see what are the characteristics of the traceable features, what is the shape of them, because not for every shape, every method would work perfectly. What is the color, size, how many tracers do we have? Are they clustering? Are they dense? And then, of course, the question is whether there is a software that implements the method that we want to use. Sometimes we want to program something new for our analysis, but not everyone has the capability or time to do this in the scope of a project. So first thing to do is to see what already exists and to which extent it satisfies the requirements that I have in my project. Luckily, there are several very good image velocimetry suites available, which I will recommend a little bit later. So we'll now discuss three methods more detail what these are. So the particle image velocimetry is one of the most popular methods. The idea of this method is that the whole field of view, the whole flow, is divided into a grid of cells of regular size, and each of these cells represents the so-called interrogation area. And for each interrogation area, the pattern of a tracer distribution is remembered. It's important that there are sufficiently many tracers in the interrogation area. If there is just one or two tracers, there is no pattern really. So therefore, PAV needs a higher seeding density. And then in the consequent frame, this pattern is being searched for around the original interrogation area in the so-called search area. The cross-correlation coefficients with different possible positions of the new interrogation area location are being calculated, and the maximum cross-correlation coefficient is considered to represent the highest probability of displacement, and on this basis, the vector of displacement is calculated. We need to make sure that we have heterogeneous density and pretty high density of traceable features for this method to work. And as a result of application of PAV, we get this instantaneous surface flow velocity field. So we have a regular grid of vectors for the whole area of interest. So everything that we do not mask out gets divided into these grids, and we get vectors for each cell in this grid. Then there is the particle tracking velocimetry method, which works in a different way, because here individual particles are being followed and not the groups of particles on a regular grid. Because of that, since particles are located in random locations, the velocity vectors are also calculated at these random locations and not on a regular grid. And matching of particles is not done based on their neighborhood, but based on them separately, or sometimes with a small number of neighboring particles, but it's definitely not the same kind of pattern which is being recorded when PAV is being applied. And in many tools which implement PTV, the algorithm of Brevis is being used. And because of that, it means that the centroids of particles are being considered as the reference points for the determining of what is the start and end location of the traceable particle. For that reason, if the particles have very irregular shapes, it may be that the trajectories are not recorded correctly. And it's very beneficial when using PTV to use particles of regular shape. PTV works well in conditions when there are not very many traceable particles in comparison to PAV. So this would be one of the first criteria for the method selection, how dense the particles, the traceable particles are in our flow. And the optical flow methods, this is a group of methods. There are several different algorithms which belong to this group. What is being followed when we apply optical flow methods is the motion of brightness patterns in the image. If some of you have background in computer vision, you probably have applied optical flow in your studies or in your work previously. And optical flow methods have not been historically used for flow velocimetry that much, so for river flow velocimetry, but in the recent years they're getting more and more popular. And the reason is that they are computationally efficient, and at the same time they can track really large numbers of features simultaneously. The two algorithms of implementing optical flow that I wanted to address in this research is the Canade-Lucas Tomassi, so the KLT approach. In classic computer vision, it would the part of it would be used the Lucas-Canade approach, but the combination of the two algorithms developed in 1981 and 1991 works better for river flow measurements in our experience. And there is Farnerbeck's algorithm, which is also applied to calculate the optical flow. but in its pure form, it's not producing the best results. So usually there are some extensions of it applied to get better quality of river flow measurement. For optical flow algorithms in general, we need just two parameters to be set by the user. This is the extraction rate, so how long do we track individual trajectories, and the block size, what is the size of the search area. This makes optical flow algorithms relatively easy to apply because there are not very many degrees of freedom, and for less experienced users, it's easier to play with and to find optimal settings for analysis in a particular study case. And optical flow algorithms were as similar as PTV, work well in conditions where there are not many traceable features. So this makes it easier also in cases when you apply artificial tracers, because you do not need that many of them, and the experiment design becomes much cheaper. So these are the three large groups of methods that can be applied at the data processing stage. How do we select the right one? So a couple of criteria I have already mentioned. The density of traceable features, for example, would be one of them. The clustering of tracers, for example, is a no-go for particle tracking velocimetry, because features have to be individual features with a defined shape and size. But there are more different criteria which can influence the selection of the best method, and we have made such a list and recommendations. Again, it can be found in chapter 9 in the book that has been recommended for this course if you're interested in this in more detail. And last but not least, the tools for image velocimetry. I have listed here four. These four because I have personal positive experience working with these tools, and also because I know the developers and I know how diligently they work on those tools. Therefore, this is something that I can recommend, and be sure that you will also enjoy using them. So there is PAV Lab for PAV. This is a MATLAB-based app, so you would need MATLAB if you decide to use it. It's a pretty old tool with a lot of use and research. It has many functions other than just velocimetry with the use of PAV. For example, it has a lot of filtering techniques, outlier detection techniques. The downside of this tool is that it's actually originally developed for the use in the lab. So not to all field conditions you would be able to apply this tool properly, but since it's open source, you can also extend it if you have desire and some programming skills in MATLAB. You can extend it such that it gets very applicable in the field conditions too. Then there is FlowVelo tool developed by Anette Eltner, who is going to be a lecturer in the following days. It's a Python app which is cross-platform. It has a nice user interface. It has several velocimetry methods implemented in it. It's also open source, so extendable. Highly recommended. It also has a tremendous image stabilization functionality. Then there is KLTAV, developed by Maddok from Newcastle University. It's a MATLAB-based app, but you can also run it, since it also can be downloaded, compiled. You can also run it just with MATLAB environment, not necessarily with the whole software suite. And it has several different interesting features in it. It implements KLT optical flow method. And there is also a big image velocimetry suite, which is called SimsFlow, developed by Robert Ljubičić from Belgrade University. It's also a Python application with a Windows interface. The interface is also only compiled for Windows, but all the code, which is doing the pre-processing, the analysis, the post-processing, also image extraction, creation of videos from your analysis results, this is all available as Python methods, so you do not necessarily need to be on Windows to use this tool too. So highly recommend this tool. It has been published at the beginning of this year, as a publication, and I have uploaded it into the list of recommended literature because it's really, really good tool. So now, hopefully, we are done with processing our data, and we can move to the last stage of the workflow, the post-processing. We see that despite the tool that we use, despite the method that we use, we will not get perfect results. And this means that we need to remove outliers if some of them appear in our results, and we need to remove spurious vectors. This can be due to insufficient seedings or at the edge of our study area. So before we do anything further, we need to remove those outliers and make sure that we fill the void. We can interpolate, for example, or we just exclude the areas for which we do not have sufficient seeding and work only with the areas where we do have enough. And we can, of course, apply some smoothing, aggregation of the data. Sometimes we just want to go to a less detail, and therefore we aggregate. Sometimes we want to produce visually more appealing results, and therefore we smooth. Very often this is like a play at the end of the whole process, just to provide something visually very appealing and to remove everything which we do not really need because it doesn't show the correct flow pattern. And when we're done with this, we visualize the end results to convey our information to our stakeholders or to our readers in our research, and also for us to be able to see whether the flow that we have calculated makes sense. Because when we just see a table with some numbers, it doesn't tell us much. When we see a picture, we can see right away, does this pattern make sense at all, especially if we combine it with the original video? What we can see with our eyes, do these vectors reflect it or not? So visualization, in my opinion, is a very important step when it's done properly, using color schemes, using the vector directions. This helps to make our research understandable and also to validate it. And the validation, except for the optical approach, we may have some reference measurements at the same time where we record our data. And these can come as surface velocities measured with some other method, like a float method. This can be velocities measured close to the water surface, either as points or as transects with acoustic Doppler current profiler, or we can have discharge. So this all we can use to compare with our results. Of course, we have to always keep in mind that every method has its limitations. So what we are comparing our calculations with is not necessarily reflecting the absolutely correct picture. So every method has some errors. So we have to consider the margins of errors in the method that we are comparing with. And if we are comparing with discharge, for example, we have to first calculate it from our surface velocity. Because otherwise we will not be able to perform this comparison directly. In any case, what we must do is to make sure that we completely georeference our data set, because we need to compare in the correct locations. Otherwise, the comparison, again, will not make any sense. And the last part of this talk are the limitations of image velocimetry and in general flow monitoring with the use of drones. First, of course, is the question is that though drones are flexible, we do not fly with them everywhere and anytime we want. Sometimes the weather conditions are unsuitable. Sometimes there are legal limitations. So this influences the applicability of the method, of course. Then if we deal with very large rivers, which is often the case, we need high resolution sensors, and they can be expensive, or they are expensive, which can be out of our budget, and that would be a limitation for our monitoring process. Then there are environmental noise constraints, such as change in illumination, glare and shadows, variations in color of the water, some flora movements, apparent ground motion due to instability. All of this environmental noise introduces errors in our calculations, and we do not always remove all of that completely, unfortunately. Then if we do not stabilize properly, or we do not remove the distortions properly, we introduce a lot of bias into the analysis results, especially in low flow conditions. So this step should not be neglected, but unfortunately, it's not always possible to completely remove, for example, all the shakiness if we have high vibration in the original data set. In this case, we just have to discard the data set and start anew. If we have a low seeding density or irregular tracer clusters, very often it's difficult to get information about the whole flow. So we will not have a complete description of the flow, no matter which method we apply and how well we calculate the vectors in the areas which are seeded properly, because interpolation does not always provide the information about the real world. It's an approximation. And we measure only surface velocities with image velocimetry techniques. So we have to find a way to come from these measurements to the depth average velocities or the discharge. There are approaches and formulas to do this, but it's still an open area of research because the world is immensely complex and it's not always possible to get exact information about the whole transect of the river where we are measuring for various reasons. And therefore, we will probably get some errors or approximations in our calculations. And last but not least, just a summary for you to take away. When we monitor flow with the use of UAS, we have these 4 steps: acquisition, pre-processing, analysis, and post-processing, and none of them can be ignored. Yeah, we cannot just do analysis and think that it's all fine. We have to pre-process, we have to post-process to get results which are close to real world and not some imaginary data. Then it's important to keep in mind the best practices. If we do not collect the data correctly, very often it will not be usable later. So pay attention to the lighting conditions, to the seeding, and so further, and then you will produce a data set that can be pre-processed and analyzed. Auto rectification is extremely important, like crucial. We need to do it both for the calculation, but also then for the validation of our results. You need to properly select the analysis method because not every analysis method will work well in the same study conditions. And before we calculate any derivatives from our data set, we need to remove outliers and other noise which otherwise would deteriorate the quality of our results. So yeah, this is all from my part. I hope it was not too much, not too fast, or not too slow and not too boring. If you have any questions, I hope I will be able to hear and answer them.
Okay. I